Welcome to this deep dive. We'll be exploring the life and work of George Gamow, a physicist who, well, seemed to have his hand in just about every major scientific development of the 20th century. You've provided a ton of material, biographical details, scientific papers. We're not just going to uncover WHO Gamow was, but really get into how his ideas shaped our understanding of, well, everything, from the tiniest nucleus to the vast expanse of the cosmos.
Yeah, what's fascinating about Gamow is that he wasn't confined to just one area of physics. He made significant contributions to nuclear physics, astrophysics, and even cosmology, all with this incredibly playful and almost mischievous approach to science.
That playful side of him really jumps out from the biographical info you sent. I mean, testing the Eucharist under a microscope as a kid, you can't make that up. I can just picture a young Gamow peering through that lens with a twinkle in his eye. It seems that questioning spirit that really set the stage for his entire scientific career.
Absolutely. It speaks to his inherent curiosity and his drive to test even the most sacred of assumptions. But it wasn't all microscopes and playful experiments. Gamow's early life in post-revolution Russia was pretty challenging. He talked about facing water shortages, dark classrooms, and even having to cut microscope glass himself for experiments.
It's amazing to think that those hardships, rather than deterring him, seemed to only fuel his determination.
They certainly did. And while he started with this intense interest in experimental physics, he eventually transitioned to theoretical physics. That's where he made his most groundbreaking contributions, particularly in the then new and mind-bending world of quantum mechanics.
Quantum mechanics, that's where things get really weird, right?
Yeah.
I'm curious what drew him to such a complex and abstract field.
Well, in the late 1920s, while working on his thesis at the University of Leningrad, he became obsessed with this puzzle that had stumped even the great Ernest Rutherford, alpha decay. It's this phenomenon where an atomic nucleus emits an alpha particle, essentially a helium nucleus.
So atoms spitting out tiny bits of themselves. Got it. But what was the big mystery there?
The problem was that classical physics just couldn't explain how these alpha particles were escaping the nucleus. Imagine a marble trapped in a bowl. Classically, it wouldn't have enough energy to roll over the edge, right? But in alpha decay, these particles were somehow getting out, as if they were tunneling through the wall of the bowl.
Hold on, tunneling through a wall? That sounds more like a superpower than physics.
That's what makes Gamow's work so groundbreaking. He was one of the first to apply the principles of quantum mechanics to the nucleus. And this idea of quantum tunneling was his solution. According to quantum theory, there's a small but real chance that a particle can pass through an energy barrier, even if it doesn't have enough energy to overcome it classically.
So instead of rolling over the edge of the bowl, the particle just goes right through it. Mind-blowing.
Exactly. And he didn't stop at just the theory. He used his quantum tunneling model to actually explain the experimental data on alpha decay, showing its predictive power. It was the first successful application of quantum theory to the nucleus.
That's huge. No wonder his work started turning heads in the scientific community. It wasn't long before he found himself working with some of the biggest names in physics at the University of Göttingen, right?
Absolutely. Göttingen was a hub for quantum mechanics research in the late 1920s. And Gamow got to work with leading figures like Niels Bohr. Bohr was incredibly impressed with Gamow's work and offered him a fellowship to work in Copenhagen, which was another major center for quantum research at the time.
From struggling with dark classrooms in Russia to rubbing shoulders with the giants of quantum mechanics in Europe, it's like a real-life scientific fairy tale.
It certainly was a meteoric rise. And after Göttingen, he went on to the Cavendish Laboratory in Cambridge, working under Rutherford himself.
Wow, talk about an intimidating environment. Rutherford was known for his strong personality and for being quite demanding of his students.
He was. But Gamow, with his own unique personality and his groundbreaking ideas, seemed to thrive in that environment. In fact, his quantum tunneling theory actually ended up playing a role in a major experimental breakthrough at the Cavendish lab.
Okay, I'm all ears. Tell me about this breakthrough.
Two other researchers at Cavendish, John Cockcroft and Ernest Walton, were working on building the first particle accelerator. And it turns out that Gamow's work on quantum tunneling gave them the theoretical foundation they needed to make it work. They showed that it was possible to use artificially accelerated protons to penetrate the nucleus and induce nuclear reactions. And their work, partly inspired by Gamow, actually earned them a Nobel Prize in 1951.
So Gamma's theoretical work had real-world implications. He wasn't just lost in abstract equations, he was shaping the future of experimental physics.
You got it. But his contributions to nuclear physics didn't stop there. While at Cambridge, he came up with another pretty radical idea, the liquid drop model of the nucleus.
A liquid drop. That seems counterintuitive. How can something as solid and dense as an atomic nucleus be like a drop of liquid?
It might seem strange. But Gamow's insight was to think about the nucleus not as a collection of individual particles, but as a cohesive whole, held together by forces similar to those that give a liquid drop its shape. He took the concept of surface tension, which you see in liquids, and applied it to the forces within the nucleus.
So instead of a bunch of marbles in a bowl, it's more like a tiny, dense droplet, held together by this nuclear surface tension. Let's start to see the analogy here.
Exactly. And Gamow didn't just propose the idea. He used experimental data on isotopes to refine his model, showing its scientific rigor. Now, there was actually some controversy surrounding the liquid drop model.
You mentioned a controversy. What was that about? Did someone else claim credit for Gamow's idea?
It's a bit complicated. Niels Bohr and Fritz Kalkar also developed a version of the liquid drop model around the same time, and their work often overshadows Gamow's contribution. The full story of who deserves credit is still debated by historians of science.
It's unfortunate that Gamow's role in the development of the liquid drop model is sometimes overlooked. But regardless of the credit, the model itself proved to be crucial for understanding nuclear processes like fission.
Right, absolutely. It helped to visualize and explain how a heavy nucleus, when bombarded with neutrons, can become unstable and split into two smaller nuclei, releasing a tremendous amount of energy in the process. It's the basis for both nuclear weapons and nuclear power.
So we see Gamow's fingerprints all over the development of nuclear physics, from explaining alpha decay with quantum tunneling to giving us this powerful model for understanding nuclear structure. His contributions are undeniable. But as you mentioned earlier, he didn't stop at nuclear physics. He also had this insatiable curiosity about the cosmos.
That's right. While he was fascinated by the intricacies of the nucleus, his scientific curiosity had a cosmic dimension. He was drawn to the big questions, like how stars produce their energy and what the origins of the universe might be. These were the mysteries that truly captivated him. It's like he was zooming out from the micro world of the nucleus to the macro world of stars and galaxies. And when he tackled these cosmic puzzles, he absolutely brought his nuclear physics toolbox with him.
I bet that toolbox came in handy. So how did he approach something as massive and complex as a star?
Well, he started by tackling the question of stellar energy production. At the time, no one really knew how stars produce the immense amount of energy they radiate. Gamow was convinced that it had to involve some kind of nuclear processes happening deep within the star's core. He even hypothesized that the energy production wouldn't be uniform throughout the star, but would be concentrated in a specific layer where the temperature and pressure were just right for nuclear fusion to occur.
Nuclear fusion. That's where lighter atomic nuclei are forced together to form heavier ones, releasing an incredible amount of energy, right?
Exactly. But the exact mechanism of how that fusion was happening in stars was still a mystery. And to really get to the bottom of it, Gamow knew he needed to bring together the best minds in physics, so he organized this major conference in Washington in 1938, specifically to discuss the problem of stellar energy production.
This is where a young Hans Bethe enters the picture, right? He's the one who would eventually solve the stellar fusion puzzle and go on to win a Nobel Prize for his work. I could just imagine the intellectual fireworks flying at that conference.
You can bet there were some intense discussions. And while Gamow himself didn't directly crack the code of stellar fusion, he played a pivotal role in bringing the right people together and setting the stage for Beth's breakthrough. He was a master connector of ideas and people.
It seems like that was a recurring theme in his career, sparking new ideas and then inspiring others to run with them. So tell me, what did Beth actually figure out about how stars work?
Bethe's work was truly groundbreaking. He identified not one, but two different cycles of nuclear fusion reactions that could explain how stars generate energy: the proton-proton chain and the carbon-nitrogen-oxygen cycle.
Whoa, two whole cycles. This was clearly not a simple problem to solve.
Not at all. These cycles involve multiple steps, with different atomic nuclei interacting and transforming along the way. The proton-proton chain, as the name suggests, starts with the fusion of two protons. And here's where it gets really interesting. That process relies on the same quantum tunneling concept that Gamow himself had pioneered to explain alpha decay.
So even though Gamow didn't solve the stellar fusion puzzle directly, his work on quantum tunneling ended up being a crucial piece of the solution. That's such a beautiful example of how scientific discoveries build upon each other.
I completely agree. It's a testament to the interconnected nature of science. And while Bethe gets most of the credit for figuring out the details of these fusion cycles, Gamow and his colleague Edward Teller continued to refine the calculations related to thermonuclear reactions, further solidifying our understanding of stellar physics.
always pushing the boundaries of knowledge. But he wasn't content to just stop at figuring out how stars burn their fuel, was he? He also wanted to understand how they evolve and eventually die, right?
You're absolutely right. He became fascinated by the bigger picture of stellar evolution. The entire life cycle of a star, from its birth in a giant molecular cloud to its eventual demise, sometimes in a spectacular supernova explosion.
Supernovae. Now, those are some seriously dramatic events. I always picture them as these brilliant cosmic fireworks displays.
They are incredibly powerful events. And Gamow, along with his Brazilian colleague Mario Schimberg, came up with this really fascinating mechanism for how stars could lose energy rapidly, which could ultimately contribute to supernova explosions.
Another collaboration, another new idea. I'm sensing a pattern here. What do they call this new energy loss mechanism?
They called it the Urca process, and this is where Gamow's playful side really shines through. They actually named it after the Casino de Urca in Rio de Janeiro, where they first met.
A nuclear physics concept named after a casino. Okay, I have to hear this story.
Apparently, Gamow was struck by how quickly money seemed to disappear from the pockets of roulette players at the casino. And he saw a parallel with this new energy loss process they were working on, where energy would be rapidly escaping from stars, carried away by these elusive particles called neutrinos.
So the Urca process was like a cosmic roulette wheel, just spinning away a star's energy. I love that analogy. It makes a pretty complex concept much easier to grasp.
And the best part is that this Urca process, which initially started as a theoretical idea, was later confirmed through observations. When a supernova exploded in 1987, astronomers actually detected a burst of neutrinos right before the explosion, just as Gamow and Schoenberg had predicted.
Wow, that's science coming full circle in a really amazing way. From a playful name inspired by a casino to a validated astrophysical phenomenon, Gamow's intuition was spot on, as usual. But didn't he also make significant contributions to cosmology, the study of the universe as a whole?
He did. Around the mid-1940s, Gamow returned to a subject that had fascinated him since his youth: Einstein's theory of relativity, and specifically its implications for the origin and evolution of the universe. He was particularly drawn to the idea of an expanding universe, a concept that was still quite controversial at the time.
So he was moving from the life cycles of individual stars to the evolution of the entire universe. I'm ready for this next chapter in the Gamow saga. Where do we begin?
Well, before Gamow, the prevailing view was that the universe was static and unchanging. But there were a few scientists, like the Russian mathematician Alexander Friedman and the Belgian priest and astronomer George Lemaitre, who were starting to challenge that view. They proposed that the universe might actually be expanding, like a balloon being inflated.
An expanding universe. That's a pretty radical idea. What did Gamow think about it?
He was immediately intrigued by the idea and saw its potential. He combined it with his expertise in nuclear physics and came up with what we now know as the Big Bang theory.
The Big Bang. That's a household name now. The idea that the universe originated from an incredibly hot, dense state and has been expanding and cooling ever since.
Exactly. But Gamow wasn't satisfied with just describing the expansion. He wanted to understand what happened in the very early stages of the universe, right after the Big Bang. He was particularly interested in how the elements, the building blocks of matter, were formed.
So he was basically asking, where did all this stuff in the universe come from? That's a pretty fundamental question.
It is, and he had this incredible insight. He proposed that the early universe was like a giant nuclear reactor, a primordial soup he called the elamlum. This ilum was so hot and dense that nuclear reactions were constantly taking place, forging the first elements, starting with hydrogen and helium.
Yellum. That's a word you don't hear every day.
It does sound a bit mystical, doesn't it? Gamow actually resurrected this old word which had fallen out of use. It originally referred to the primordial substance from which all matter was thought to be formed. Gamow saw it as a fitting description for the incredibly hot, dense state of the early universe, a state where matter was constantly transforming.
It's like Gamow was weaving together science and mythology, bringing this ancient idea of creation into the realm of modern physics. I love that.
He had a real knack for finding those connections between seemingly disparate ideas. And as usual, he didn't work alone. He collaborated with two brilliant physicists, Ralph Alpher and Robert Herman, to develop detailed calculations about how the elements could have been formed in the early universe.
So they're crunching numbers, trying to simulate those first few moments after the Big Bang.
Yeah.
And see what kind of elements would emerge from the ilum.
Exactly. And those calculations led to a prediction that would have profound implications for cosmology. They predicted that the Big Bang should have left behind a faint afterglow, a cosmic microwave background radiation permeating the entire universe?
Cosmic microwave background radiation. So like an echo of the Big Bang, still detectable billions of years later.
You got it. They predicted that this radiation should have a temperature of just a few degrees above absolute zero, a faint remnant of the universe's incredibly hot beginnings. It's hard to overstate how groundbreaking that prediction was.
So did they immediately build a telescope or some kind of instrument to try to detect this cosmic echo?
Funny enough, they didn't have to. In 1964, two physicists, Arno Penzias and Robert Wilson, stumbled upon this cosmic microwave background radiation completely by accident. They were working on a radio antenna for a completely different project and kept picking up this persistent hiss they couldn't explain.
Wait, so the Big Bang's afterglow was discovered by accident. That's amazing. What did Gamow think about all this?
It's actually a bit of a bittersweet story. Gamow and his team had made this remarkable prediction years earlier, but their work wasn't widely recognized at the time. He was obviously thrilled to see his prediction validated, but also a bit frustrated that he didn't get more credit for it. Penzias and Wilson ended up winning the Nobel Prize for the discovery in 1978.
So Gamow laid the theoretical groundwork for one of the most important discoveries in cosmology, yet didn't share in the Nobel Prize glory. It seems like a recurring theme with him, sparking ideas that lead to major breakthroughs, but not always getting the recognition he deserved.
It does seem that way. But despite those missed opportunities for accolades, he continued to push the boundaries of science, never shying away from a good debate. In fact, he famously disagreed with the prominent astrophysicist Fred Hoyle, who was a proponent of the steady-state theory.
So we have a cosmic clash of titans. Gamow, the champion of the Big Bang, versus Hoyle, the defender of the steady state. It sounds like an epic scientific showdown.
It was. Hoyle argued that the universe was eternal and unchanging, with new matter continuously being created to maintain its density. This was a completely different picture from Gamow's Big Bang, where the universe had a definite beginning and was constantly evolving.
And how did Gamow respond to this challenge to his Big Bang idea?
Well, he was never one to back down from a scientific debate, especially when he was convinced he was right. He argued passionately against the steady-state theory, pointing to the evidence from the expanding universe and the cosmic microwave background radiation as support for the Big Bang.
It seems like the discovery of that cosmic background radiation really tipped the scales in favor of the Big Bang. It's hard to imagine how a steady-state universe could produce that kind of afterglow. Did Hoyle ever come around to accepting the Big Bang?
While Hoyle never fully embraced the Big Bang, he did make significant contributions to our understanding of how elements heavier than helium are formed in stars. His work on stellar nucleosynthesis helped explain where all those heavier elements we see in the universe came from.
So even though they disagreed on the fundamental origins of the universe, both Gamow and Hoyle made crucial contributions to our understanding of how matter is created and transformed. It's a reminder that science often advances through both collaboration and healthy debate.
I think that's a great point. But speaking of disagreements, it's interesting to note that Gamow himself, despite his expertise in nuclear physics, was actually excluded from the Manhattan Project.
The Manhattan Project, the top-secret effort to build the atomic bomb during World War II. That seems strange considering his background. Why was he left out?
It was probably a combination of factors. His Russian origin likely raised some red flags during those tense Cold War years, and his personality, which could be quite playful and irreverent, might not have fit the mold of the very serious and secretive Manhattan Project culture.
So even a brilliant mind like Gamow's couldn't escape the political realities of the time. It's a reminder that science doesn't exist in a vacuum. It's always influenced by the social and political context of its time.
You're absolutely right. But even though he was sidelined from the Manhattan Project, Gamow still contributed to the war effort. He worked as a consultant for the U.S. Navy, focusing on conventional explosives.
From the mind-bending world of nuclear physics to the more practical realm of conventional explosives, what a change of pace.
It might seem like a step down, but who knows what kind of mischief Gamow might have gotten into working with explosives. And besides, even in that role, he still had opportunities to connect with other brilliant minds. In fact, he even got to discuss physics with Einstein during his consulting work.
Wow, Gamow and Einstein talking physics while working on explosives for the Navy. That's an image I won't soon forget.
Yeah.
Do you know what they talked about?
There's a famous anecdote about one of their conversations. Einstein confided in Gamow that introducing the cosmological constant into his equations of general relativity was the biggest blunder of his life.
Einstein admitting to a blunder. That's incredible. It makes him seem a bit more human. knowing that even the greatest scientific minds make mistakes.
It does. It's a good reminder that science is a process of trial and error, and even the most brilliant scientists are constantly revising and refining their ideas. But speaking of brilliant minds and new ideas, we haven't even touched on Gamow's foray into the world of biology.
Oh, right. After tackling the mysteries of the atom, stars, and the universe itself, he decided to dive into the complexities of life. What started that transition?
It seems that the discovery of the structure of DNA in 1953 by James Watson and Francis Crick really captured his imagination. He was fascinated by this idea of a genetic code, a set of instructions embedded within DNA that determine the traits of living organisms, and he was especially interested in the challenge of deciphering that code.
DNA, the blueprint of life. That's a pretty big leap from the world of physics. What drew a physicist like Gamow to this seemingly unrelated field?
Well, for one, he was close friends with Max Delbruck, another physicist who had made significant contributions to biology, particularly in the study of bacteriophages, which are viruses that infect bacteria. This friendship exposed Gamow to the exciting world of molecular biology.
So he had this insider's view of what was happening in biology. But it wasn't just the friendship, right? There must have been something about the intellectual challenge of DNA that really appealed to him.
Absolutely. Remember, Gamow was always drawn to puzzles and codes. He saw this challenge of figuring out how the sequence of building blocks in DNA, called nucleotides, could translate into the sequence of amino acids that make up proteins, as a kind of cryptographic problem.
So he was approaching the genetic code like a secret message waiting to be decoded. I love how he brought that unique perspective to everything he explored.
That was Gamow's genius. He could see connections and patterns that others missed, and he wasn't afraid to apply his knowledge and skills from one field to another. And he made some important contributions to our understanding of the genetic code. For example, he was one of the first to propose that the code was a triplet code, meaning that each amino acid is specified by a group of 3 nucleotides.
He was on the right track, even if he didn't crack the entire code himself. It seems like a recurring theme in his life, planting seeds of ideas that would later blossom into major scientific breakthroughs. But it's important to note that he wasn't just a brilliant researcher. He was also passionate about sharing the wonders of science with a wider audience. That's where his famous Mr. Tompkins stories come in, right?
You got it. Gamow had this incredible gift for explaining complex scientific ideas in a way that was both entertaining and insightful. He created these whimsical stories about a bank clerk named Mr. Tompkins, who finds himself transported to dreamlike worlds where the laws of physics are drastically different.
I heard about those stories. They sound like a delightful blend of science and fantasy. What kind of physics-bending adventures did Mr. Tompkins have?
Oh, all sorts. In one story, he visits a world where the speed of light is so slow that he can actually experience relativistic effects firsthand. In another, he explores a world where quantum effects are magnified, leading to all sorts of bizarre and counterintuitive phenomena.
It's like taking a guided tour of the universe's weirdest and most wonderful corners, all through the eyes of this ordinary bank clerk. No wonder those stories became so popular.
They were a huge hit, but it's interesting to note that Gamow initially struggled to get those Mr. Tompkins stories published. He faced rejections from several magazines before finally finding a home for them in a British science magazine.
Even a brilliant scientist like Gamow had to face rejection. It's a good reminder that persistence is key, even in the world of science writing. But once those stories found an audience, they really took off. They were translated into multiple languages and introduced generations of readers to the beauty and wonder of physics.
Gamow's legacy is really quite remarkable. He made groundbreaking contributions to nuclear physics, astrophysics, cosmology, and even biology, all while maintaining this infectious sense of playfulness and wonder.
And through his popular science writing, he shared that sense of wonder with the world, inspiring countless people to explore the mysteries of the universe. It's like he was saying, science isn't just for scientists. It's for everyone.
I think that's a beautiful way to sum it up. George Gamow's life was a testament to the power of insatiable curiosity, a playful approach to complex questions, and a deep desire to share the beauty of science with the world. What stands out to you from this deep dive? His groundbreaking work on quantum tunneling, his playful explanation of the Urca process, his bold vision of the Big Bang, or perhaps his charming Mr. Tompkins tales?
It's hard to choose just one. But I think what I find most inspiring about Gamow is his relentless curiosity and his ability to see connections between seemingly disparate fields. He never stopped exploring, never stopped asking questions, and never stopped sharing his love of science with the world.
And that's a lesson we can all learn from him. The universe is full of wonders waiting to be discovered. And as Gamow himself might say, the key is to never lose your sense of wonder. Keep exploring, keep questioning, and keep pushing the boundaries of what we know.